there are different ways of representing a set. The first one is the roster method, which is basically set A consists of 1, 2, 3, 4 and 5 elements. So that's quite a simple, straightforward definition, formally called the roster method. Then you have the set builder method, which basically is set A consists of all x such that x is a result of function cx. So instead of giving the values of A directly, we are building up the set A by cx, which is a function of x. So let's look at a quick example of this. So an example could be x is a natural number and less than 7. So the set A consists of 1, 2, 3, 4, 5 and 6, because when you actually find the value of x given these conditions here, you find that natural numbers, so it should start with 1, and then x is less than 7, so it can be 1, 2, 3, 4, 5 and 6, and so set A is represented by these numbers. Now the difference is when the members of set A are clear cut, you can define all the members, but if the relationship is more complex or the numbers are larger, then you normally used the set builder method for representing a set. Okay, we have different types of sets. First one is an empty or a null set, denoted simply by curly brackets. So an example could be set of even prime numbers excluding 2, and we know there are none. Another one could be singleton set, which has only one value. So again, the example could be set of even prime numbers. Then we have finite sets whose elements can be counted and are finite. And as a corollary to the finite set, we have the infinite set. An example could be the set of all irrational numbers between 1 and 2. Equal sets. Two sets are said to be equal if all the elements of one set belong to the other and the other one has no extra elements in it. So in this example, set A has ABC as members and set B has the same but in a different order. So we say that set A is equal to set B, or simply A equals B. Subsets. Subset A is said to be the subset of another set B if all the elements of set A are included in set B. And this is the symbol that's used by the set notation to represent that A is a subset of B. Of course, we don't have to worry too much about symbols because the test is all about application of concepts, but it's good to know how these symbols work. So here's an example of a subset. A consists of elements A, B, C, and B consists of A, B, C, D, and E. Hence, all the elements of A are included in B, and we say that A is a subset of B. Another concept is the universal set. So if we had three sets, A, B, and C, and A contained elements A, B, C, B contained B, C, D, and C contained C and D, then the universal set is basically a sum of all the elements of the individual sets. Okay, coming to the more interesting part, here we're going to talk about set algebra. We're going to take a look at some formulae that might be useful in solving problems that you get in the test. So the first one is the so-called commutative law. We don't need to worry about what the law is actually called so long as we understand the basic concepts. So A union B is equal to B union A, and A intersection B is equal to B intersection A. Now this symbol that you see here, the U is union and the inverted U is intersection. Again, it doesn't matter what the symbols are as long as we are clear on what they are trying to say. Then we have the associative laws for sets A, B and C, which essentially say that A union B union C is the same as A union B union C, irrespective of the order of the operation. So this essentially is saying that A union B, if you do that first and then do a union with C, the result would be the same as if you do B and C first. Now you need to keep in mind that a union is like an addition, so you're adding A, B and C, and the order in which you add doesn't really make a difference. So it might become more clear if we actually draw some sets. So this is set A and I'll use a different color for set B and a different one for set C. So essentially A union B union C is the sum of these three circles together, and it doesn't matter in which order you add them. Now let's look at A intersection B intersection C. So in this case you are doing the B and C intersection first, so let's see what you get. So this is the area that represents B intersection C, and this area we need to find what is common with A, which would represent the intersection of A and B intersection C. So essentially this is the area we're talking about. So the left hand side here, A intersection B intersection C, represents the shaded area, essentially this one. And now let's look at the right hand side. So we do A intersection B first, so that would be this whole area. And then we do the intersection of the result with C. So what is common between A intersection B, which is this area, and C? And the answer is again this portion, the same portion that we got earlier on the left hand side of this equation. So if we actually draw these as Venn diagrams, it's very easy and intuitive to understand what the set rules are saying. Some more important laws, identity laws. The first one is essentially this symbol represents a null set, which basically means there's nothing in it. So A union the null set is A, because you're not adding anything more to A. The null set represents nothing. And A intersection U is equal to A. Now U is the universal set that we previously discussed. So what's common between A and the universal set is essentially the elements of A itself. And then we have the famous Demorgan's laws. There are other variations of these as well, but we'll just focus on what we need for the test. So the first one says A union B complement, the comma here represents a complement, is equal to A complement intersection B complement. Now complement is basically, A complement is whatever is not in A. So if we actually draw these and see how it works out. So let me clear this first. So A union B, so this is my A and this is my B, and I'll just draw the universal set. So A union B is represented by, let me use the blue line, this, right? So this is my set A, this is my set B. So the blue lines represent A union B. Now the complement of these, A union B complement, would be whatever is not there in A or B. So this U is the universal set, which basically means everything in this rectangle. So we've got A union B represented by the blue lines, and A union B complement would be something represented by these lines here. Essentially everything that's outside of these two circles. So the black lines represent the equivalent of A union B complement. So let me just write it here. So this diagram now is A union B complement. And now if we go further, let's try to find what is A complement. So this is my set A, this is my set B, and this is my universal set. So what is A complement? Everything that is not part of A. So let's again denote that by the blue. Okay, I got it finally. So the blue lines here represent A complement, which means everything that is not in set A. And now let's look at what is B complement. So I draw my two sets again. This is A, this is B, and this is my universal set. So B complement would be everything that is not in B. So the area represented by these blue lines again. So here we have we complement everything outside of this shape basically. Let me draw that in a different color so that it's clear. So this is my set B, and B complement is anything outside of this green circle. Now I've just redrawn this figure so that the lines are in the same plane, and now it is easier to see what is common between this figure, which represents A complement, and this figure which represents B complement. It's essentially everything outside of the two circles. So just to draw it again. So essentially this figure represents A complement union B complement, the shaded blue lines, and our original figure, the black lines here, represent A union B, the whole complement. And as you can see, this is really equivalent. So once you've actually drawn these rules in a Venn diagram, it'll be easy and intuitive to see that these are actually true. So this example was for the first one. Similarly, you have the other Demorgan rules, which is A intersection B, the whole complement, is equal to A complement union B complement. So if you just draw these diagrams like we've done for the first rule, you'll find that it's quite easy and intuitive to see how it works. Now some important results. Some of these you might need to use as direct application in a problem. So the first one is A minus B is equal to A intersection B complement. So let's take an example. This is set A, this is set B, and this is our universal set U. So A minus B essentially is take away everything which is in A which is not in B. It's essentially a minus operation. So in terms of Venn diagram, this blue line, this blue figure essentially denotes A minus B. So the common part, which is this shaded part, is common to A and B, has been taken away. So A minus B is essentially like a mathematical A minus B. So what we're left with is this figure denoted by the blue line. Now this is equal to A intersection B complement. So let's first find what is B complement. So we'll draw another figure for that. So this is A, this is B, and my universal set. So B complement is whatever is not there in B. So essentially the area denoted by the blue line. Everything that is not there in B is B complement. So what's common between this and A? What is in A and also in the area represented by the blue lines? Essentially this is the area denoted by this line. So you can see the shape is essentially the same as we found earlier. So this is equal to this. So similarly we have other laws. B minus A is equal to B intersection A union, and so on and so forth. We don't really need to remember or recall or know the meaning of this, because most of the problems in the test can be solved by using these Venn diagrams. And when you use Venn diagrams, it's all very intuitive what the question is asking. So let's start diving straight into the problems. We'll start with a simple problem. R is a set of positive odd integers less than 50, and S is a set of squares of the integers in R. How many elements does the intersection, note intersection, of R and S contain? So let us list down what are the elements of R, curly brackets. So R is a set of positive odd integers. So R is 1, 3, 5, 7, 9, and so on till 49. And S, let's use a different color to represent S, is essentially the squares of each of these. So square of 1 is 1, square of 3 is 9, square of 5 is 25, square of 7 is 49, square of 9 is 81, and so on till 49 square, which I do not need to calculate, so I will not do that. So essentially the question is asking what is the intersection of R and S. So which are the common elements that exist in both R and S? So we just have to look at it visually. So 1 is common, 1 is right here, 3 is no, 3 isn't there in the second set, 5 isn't there in the second set, 9 is, so 9 is the second one. And then can you see any other element? You know that 25 is a square of 5, but 25 as a number would also exist in R, because R is from 1 to 49, all the odd numbers. And similarly 49 is right here, so this is a common element as well. So essentially you get 1, 2, 3 and 4 common elements. So the answer is 4. So this was a simple example just to get you started. Let's take a few more complex examples. Okay, moving on to our next example. Here P and Q are sets of integers. P triangle Q, triangle is a symbol. It's not a symbol really of set notation, but it's a symbol specific to this question. So P triangle Q denotes the set of integers belong to P or Q but not both. It's critical to read the question properly because otherwise it's very easy to make a silly mistake, and as you know, making a mistake in the first 10 or 15 questions is quite serious for your overall score. So if P consists of 10 integers and Q of 18 and 6 are common between P and Q, then how many integers are there in P triangle Q, which basically means in P or Q but not both. So let's try to solve this using our Venn diagrams. I always find Venn diagrams are much easier to use and to understand, and when you get the answer you're sure that that's the right answer, because what you typically use is basic logic. So here is my set P and here is my set Q. P and Q. In this case I do not really need the universal set, but for the sake of completeness let me put the universal set here. So let's put the information from the question into this diagram. So what do we have? If P consists of 10 integers, so P has 10 integers, so I'll just put 10 here. I'm putting it on the edge of the circle. It's a notation, you can use any notation that you feel comfortable with, but essentially putting 10 on the edge of the circle means P has these 10 elements, and some of these 10 can be common with Q or with another set X, Y or Z. So these 10 represent the complete set of elements within P. Q consists of 18 elements, so let me put 18 on the edge here, and 6 are common, they are in both P and Q. So let me put 6 elements right in the middle. So the area in the middle represents the common area between P and Q. So now we've put all the information from the question into this Venn diagram. So the question is asking us to find P triangle Q elements that belong only to P or only to Q but not to both. So now from here, from the Venn diagram, we know that 10 elements belong to P and 6 belong to P and Q. So how many elements belong to only P? Now that is represented by this area as we saw earlier, and this is essentially 10 minus 6, which is equal to 4. So just to make it more clear, let me rub this. So essentially there are 4 elements here, and similarly the number of elements that belong only to Q and not to P is 18 minus 6, which is equal to 12. So again, just to put it a little more neatly, let me take out this. So 18 minus 6 was 12. So now from this diagram we know clearly that there are 4 elements that belong only to P and not to Q. 12 belong only to Q and not to P, and 6 in the middle belong to both P and Q. Hence P has a total element of a numbering 10, which is 4 plus 6, and Q has 18, which is 12 plus 6. So let's go back to the question and see what we want. Essentially what we want is P triangle Q, which is elements, the number of integers that belong to P or Q but not both. So which essentially is equal to 4 plus 12, 16. And do we have any answer choice which is 16? Great. So the answer is 2. So this was a simple application of putting the information in the form of a Venn diagram and then arriving at a question, arriving at the correct answer. Now with this kind of working, there is no way you can go wrong because it's all clearly mentioned here. There's no chance of making a silly mistake here. So if we look at the formal solution, it's essentially using some of the formulas that we learned earlier. This is the alternative way of doing it and equally good depending on your comfort level. So let's now have a look at some more complex question, something that you might get in your real test towards the end when questions generally become more difficult. At a birthday party of Sherry, a baby boy, 40 persons chose to kiss him and 25 chose to shake hands with him, and 10 people chose to both kiss him and shake hands. How many people turned out at the party? Now again, this question is very similar to what we did in the previous one. We represent this information in a Venn diagram, or we can solve it using the set algebra without if you cannot draw a Venn diagram for whatever reason, or you're comfortable using direct equation formulae, then it simply depends on your choice. But let's look at how we solve this question using Venn diagram, and then we'll look at how we solve this using set notation. So the thing about Venn diagrams is that we need to first represent this information in a Venn diagram. So what do we have here? We have 40 people kissed and 25 shook hands. So let me draw 2 circles. So K denotes people who kissed and S people who shook hands, and for the sake of completeness I will draw the universal set. So let me just write the numbers 40 and 25, because 40 people we know kissed him and 25 shook hands, and we also have that 10 people chose to both kiss him and shakes hand with him. So where does 10 go? Yeah, in the center. So how many people out of these 40 that only kissed him and not shook hands with him? So that's 40 minus 10, which is 30. And similarly, how many people shook hands with him without kissing him? That's 25 minus 10, which is 15. So here we have 3 numbers now, 30, 10 and 15. 30 represent people who only kissed him, which means there is nothing common between these 30 and these 15 who actually shook hands with him. So just to draw the diagram, so the blue figure represents people, 30 people who only kissed him and did not shake hands with him. The other figure here represents 15 people who only shook hands with him and did not kiss him, and the shape in the center represents people who did both. Now the question is saying how many people turned out at the party. We know that everyone at the party either kissed him or shook hands with him. So essentially all the elements, all the people are represented by set K and set S. There is no one that did neither, because if that were the case the question would specifically state that. So here we need to find out how many people turned out at the party. So the people who turned out at the party would be people who either kissed or shook hands or did both. So essentially the sum of these three numbers, 30 plus 10 plus 15, which is equal to 55, which is the choice you have here. So let's see how this question might be solved by using the set algebra. Here we have the solution by the alternative method. So it says that number of people who kissed is 40, number of people shook hands is 25. Now number of people in the intersection of A and B sets is 10, and this is the formula we use. Number of people A union B is equal to number of people represented by set A add to number of people in set B minus number of people which are common. Essentially this is because in the previous set diagram, if you look at, you'll see that you'll be double counting. If you added K plus S, this area in the middle, this area would be double counted because it would be counted as K, part of K as well as part of S. So in the set algebra, this is the area you need to take out when you're adding A and B. Essentially the same result as before. Moving on to the next problem. Here this is slightly more complex than the ones we've discussed before, but using the same concepts. So let's have a look at what the problem says. In an exam, 43% passed in math, 48% in physics, and 52% in chemistry. Now when the problem says 43% passed in math, it means they could have passed in other subjects as well, which in this scenario, in this question, are physics and chemistry. So again, it adds only 8% passed in all the three, 14% in math and physics, 21% in math and chemistry, and 20% in physics and chemistry. The total number of students is 200. How many students passed in math? So the way to do this kind of a problem is like we've done earlier. Try to represent the information in a Venn diagram. You could also use set notation, but when you are dealing with three different sets, math, physics and chemistry, it might get a bit more complex, so recommended to use Venn diagrams for this. So let's try to put the information in the form of a Venn diagram. So now we'll need three circles, each representing physics, chemistry and maths. So I've got my P, C and M, And as usual, for the sake of completeness, let us also draw the universal set, which is represented by the number 200 here. So how many so let's try to put all the information in this question into this diagram and see where we go. So the first piece of information is 43% passed in math. So let me try to use different colors for the three. So math is the one at the bottom, and you have 43. 48 passed in physics. 48 and 52 passed in chemistry. So there you go. 8% passed in all the three. So 8 goes in the center, the area that is represented by the intersection of P, C and M, the area in the middle. And what else does it say? 14% passed in maths and physics. So M and P is 14. So I'll write 14 here, which is the border of P and M, because 14 passed in physics and maths does not mean that some of these 14s could not have passed in chemistry. So we'll see how this information plays a role in solving the problem, but let's just first put all the information into the Venn diagram. So similarly, we have 21% passed in math and chemistry. So I'll put 21 here, and 20% in physics and chemistry, so I'll put 20 here. Okay, so now we've put all the information in the form of the Venn diagram. Now you see that this diagram has 3 circles, 3 sets versus the 2 that we've seen so far. So just looking at the information elements one by one, we have 8 passed in physics, maths and chemistry, and 14 passed in physics and maths. So how many passed only in physics and maths and not in chemistry? That would be 14 minus 8, which is 6. So 6 students passed only in physics and maths and not in chemistry. 14 students passed in physics and maths, and only 6 passed only in physics and maths. So you need to be careful about the overlap when you talk about sets. So the overlap concept is the one used to confuse students the most, and once you get that clear in your head, this Venn diagrams and sets and any questions around those would be a piece of cake. So again, let's look at physics and chemistry combination now. So we have 20 students who passed in physics and chemistry. So when the question tells us that 20% passed in physics and chemistry, we'll deal with the percentage bit a little later. So just so that we keep that in mind, I'm just going to say this universal set is 200, whereas the other figures are talking about percentage, so we'll have to take that into account while selecting the final answer. Okay, so going back to the question, it says 20% passed in physics and chemistry. It doesn't say how many of these 20 also passed in math, but we can derive the whole set of information by using this 8, which is stated in the question. Only 8% passed in all the 3. So now we know that 8% students passed in physics, chemistry and math, and 20 passed in physics and chemistry. So how many students passed only in physics and chemistry and not maths? That would be 20 minus 8, like we did for physics and maths earlier. So this area, let me just draw that out for more clarity. So this area is 20 minus 8, which is 12, and this area represents students who passed in physics and chemistry but not in math. So similarly, how do you find the students who passed in math and chemistry but not in physics? So we have these numbers: 21, 8, 21 minus 8, which is 13. So let me just write 13 here, and 13 represents this area, which essentially is the percentage of students who passed in chemistry and math but not in physics. So if you look at maths only here, how many students passed in math only would be given by this part of the figure. So essentially the information we have now is that 43 students passed in math, but some of those also passed in physics and chemistry, or both. Now from this information and the other pieces of information, we've derived that 6% students passed in physics and math alone and not in chemistry, 8 in all of them, and 13 in only chemistry and math but not physics. So what we need to do is to find the number of students represented by this green shape, and this is essentially 43. 43 represents this whole set of students who pass in math, essentially this circle here. This whole circle of M is represented by 43, out of which we have to take out this, this and this to get our green area, which is the percentage of students who passed in math alone, and that is 43 minus 6 minus 8 minus 13, which is essentially equal to 16. So looking at the answers, 16 is right here, and that's great, but is this the right answer? Well, that's where the test tries to confuse you and get you into making errors, silly errors, and thereby losing that 99 percentile. But anyways, if you're careful, you see that the number of students who took the exam is 200, and all this while we've been talking about percentages. So this answer 16 is essentially 16%. So if the number of students who took the exam was 100, the answer would be 16, because 16% of 100 is 16, but 16% of 200 is 32. So 32 is the correct answer. So hope you enjoyed this session. Please do leave your feedback so we can design our future sessions as per what you need. Thank you very much.